Hello, welcome to my discussion on improper integrals. This is the third time I've tried recording this. Hope I get it right because the last one was a long video and I had to redo it. And here we go. In the past, you've worked with integrals that are of two different types. We had two different restrictions, and that is the domain of the integration was finite. Like the range of the integral that went from a to b, where a is finite and b is finite. So that was one restriction we had. And the range of the integrand is finite. In other words, we didn't have any asymptote behavior, where let's say if this is our graph, and we'll make a boundary for our lower bound and our upper bound, and that we didn't have a graph that had this kind of behavior, where it would rise up to a positive infinity and then reappear from the negative up to a value of which there's a region in the middle that is undefined, where you have to make this, where these are actually two separate curves that have to be dealt with separately, boundary from here and a boundary from here, but you haven't seen those yet. And so these types of integrals are improper integrals, and we have to do a few minor transformations to make them mathematically correct and to solve them. And we do that using limits to help us arrive at a result. If the limit converges to a value, that is our result of our integral. But sometimes it doesn't happen. If the limit fails to exist, then there is no integral for up through infinity or negative infinity even. Sometimes that happens. There's a lot of functions that fail to exist. For the most part in this chapter, what we see do converge to a value. In chapter 10, we'll see the ways how you can tell if they will converge or diverge. And so here's a picture I pulled from the textbook that shows a graph. And as x becomes large, or as our upper boundary of our integral becomes large, the amount of area that it adds under this curve becomes insignificant and does not make a substantial contribution to this area. So this curve would actually have a finite area under it, even though the boundary moves up to infinity in this direction. And so these types of integrals, improper integrals that have an infinity or negative infinity in for the boundaries, are called type 1 integrals. You don't really need to know the type 1 or the type 2 that you'll see in a moment. Just know that when you see an integral that has an infinity in the boundary, like these, or doubly bad, these guys, that they're improper integrals, and you need to do a transformation. And what the transformation is that you turn these boundaries into variables, like b. Whereas b is a limit approaching infinity. And then you perform this integral and substitute in the case for where b approaches a very, very large number, and see if you converge to a number or see if it diverges. Same is true for a negative infinity. Now when you have a negative infinity to a positive infinity, you need to break it up, and there's some point c in between here that you'll need to separate this. If the function is always defined and it's a smooth continuous curve, usually you do 0 because a 0 on a boundary of an integral typically causes stuff to disappear because you end up multiplying by 0 or substituting a 0 in for x. So 0 is a pretty smart number to use if you don't want to do a whole lot of math work. You could probably use other numbers with more effort, but usually it's 0. If there's an asymptote in between here, like going like this, like some curve that makes this kind of shape, you'll need to use that value as your C. And those types are the type 2 improper integrals that you're going to see in about 10 or 15 minutes, unless you skip ahead to that. And so here's our first example. You write it as a proper integral using a limit towards infinity. And I didn't write that in there. That's supposed to be a b, from 0 to b. And you evaluate this integral. What type of integral does this look like to you? You've probably seen this before. You're seeing we got an x squared, and we have this 1 here, which you can think is, that's a 1 squared. Could be 1 squared. It has a square root. So does this x square and everything then? That sort of looks a little bit trigonometric. You're probably having visions of sines and cosines going on, and you'd be correct. It turns out that this is actually an inverse trigonometric integral. But you can solve that the hard way, or you can just look up in the back of the book, which is at this point what I'd prefer you to do, because speed is the key. The integral from dx over x squared plus 1 is equal to the inverse tangent of x. And so we substitute that integral into our limit from 0 to b as b approaches infinity. I should have wrote an x there. That should be an x. And you substitute it in, and the inverse tangent of 0 is equal to 0. So you're going to basically have, and the inverse tangent of a very large number is pi over 2. So you end up with pi over 2 minus 0, which is just pi over 2. So there's a little bit of a mistake there with that b and that x being not drawn right. But that's all right. We got more examples. Here's another one, dx over square root of x. It contains the points 0 and 1, but the function is undefined at 0. It's a division by 0. So the right-handed limit must be applied to keep ourselves clear of this 0, which is hazardous to us. So let's solve this indefinite integral. And so this is a power rule integral that you solve this, and you get the integral of x to the negative 1/2 becomes x to negative 1/2 plus 1, which is the positive 1/2 power of x, or square root of x. And we divide by negative 1/2, which is a negative 2. So negative 2 times square root of x, that's your integral, plus c. And so what would this limit look like as we approach this? Well, we have this 0, that's the hazardous one we have to avoid, but we also have a square root symbol here, and we can't have a negative number in the square root, so we have to approach this 0 from the positive side. And so this is our right-handed limit. Notice we've got this positive symbol up here that we are operating with our limit towards. And so just simply substituting in the solution to our integral with our boundaries, we basically substitute in 1 and b. So 2 to the square root of 1 minus 2 to the square root of 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0 That's our 2 minus 0. So this integral would be 2 from 0 to 1. How about that? That's how you do these. Here's a wicked one. We have a negative infinity to a positive infinity. So we have two infinite boundaries. We have to find the entire area under the curve. So we can't take a limit to two separate values simultaneously. So we need to break this up into two integrals. Remember I said 0 is a good central value to use because oftentimes it makes things cancel out nicely. Well, that's what we'll do. Negative infinity to 0, and then a second integral from 0 to positive infinity. And now we can put our limits. And so our one limit is going to be to approaching as b approaches negative infinity. The other one is going to be as b approaches positive infinity. So that first one I said is on the left, negative infinity, and then b approaches positive infinity. And these, for some reason, when I printed these out, the boundaries did not draw. So I'm going to have to do them manually here. Sometimes when you get a large document, strange things happen. And so this is what our limit would look like. And we solve this indefinite integral. We solve by a substitution. You make a substitution of u equals x squared plus 1. The derivative of u is going to be 2x times a very small region of dx. And we have our, if we solve for dx, you could think of it as like solving for it. It's equal to du over 2x. And what you end up with is that the 2x's cancel out. You end up with the integral of du over u squared, which is right here. Basically, the integral of u to negative 2 power. You integrate to raise this by a dimension. This negative 2 gets raised up to be a negative 1, and it's divided by this number you raised it to, negative 1. So you could rewrite this as negative 1 over u plus c. That's our integral. Now we substitute that integral back into our boundaries. Well, first we have to put our u of x squared plus 1, u equals x squared plus 1 back in. I made that same mistake when I did it last time too. That's weird. So anyway, I forgot about. You have to make this a function of x again. And now you substitute this blue function back in to your limits. So you no longer have this intimidating looking limit and integral at the same time. Now you have this limit of this function, and you have this bound interval from 0 to b. So it's actually going to be four functions. It's going to be this with 0 in for x squared, and then b minus b for x squared, and then you do the same for the other limit. So you end up with four terms altogether. And I solved them separately. The first limit is solved on this line right here, and the 0 squared plus 1 is in the denominator, plus the b squared plus 1. That's plus because this function is actually negative. So minus a negative is a positive. And we put in so when you substitute in for 0, this becomes, this left-hand side becomes a negative 1. You put a very, very large number in for b on this right-hand side, and you end up with a number that's 1 on top and a very, very large number to the denominator, which is going to approach 0. So this is going to be basically like minus 1 plus 0. Now on the lower one, the second limit, you substitute in a very, very large number for b, and you end up with a very, very small number, just like we did in the previous case. That's going to be 0 plus the 0 plus 1. You add those two up, -1 and +1, you'll get that the total integral, the area under the curve, is 0. And another reason it's 0 is if you look at this function, if you graph it, it's an odd function. It crosses at 0, and it goes up, and then it goes back, levels flat, and the other side is mirror imaged. It goes down, goes back up, and levels out. And if you take your boundaries to be equal distance from the center, they're going to be negative of each other. This side a negative area, and the other side would be the positive area. And they would always equal to 0 no matter what the boundaries are, if these two boundaries are like negative a and positive a. So that's why this one ended up being 0 too, is also because it's an odd function. In this case, a approached infinity. So no cumulative area under the curve. The area under the positive side is 1. The area under the negative side is -1. And so here's a special integral, and that's from 1 to infinity of dx over x to the p power. And this is a bit of a special case here of a family of integrals that you can solve very quickly by looking at a reference here. Now, I'll show you the logic behind it. And to really see this, you have to take a look at the integral of dx over x to the n power. And that is when n is equal to, and I rewrote this integral slightly to where up here the n is in the denominator, and here it's in the numerator. And so when n is a negative number, -1, I mean, it's a special case of where the integral will be equal to natural log of x plus c. But the area that we're going to be looking at is when n is equal to -1, or x, or in this case, for the top function, the equals a +1 in the denominator. That integral, or if this is not equal to 1, to some other number, any other number, this would be an integral that follows the power rule. And so what happens is that we have to dodge this this certain number that causes this integral to not work. And so, and that number is going to be 1, because it's in the it's going to be 1 because in this case the x to the n is in the denominator. So that'll be when n equals 1 in that case, you're going to be looking at this type of integral, not this one. And so we have two domains of P, and there's going to be the group above +1, and there's a group below +1. And in these domains, the integral is a power rule integral. Okay, makes sense. You know, if n is equal to 1, that's what our integral will be. And of course, if you want to rewrite this slightly, if you're more comfortable with saying x to the n, we brought it up to a numerator to make it positive. Then you might recognize this as x to the positive n plus 1 over n plus 1. But we drew it in the denominator mainly to make the math work out a little bit better. And try to to simplify it a little bit. And so we have this power rule integral, and with these boundaries of 1 to infinity, I write it as a limit. And that's this on the bottom line here, is this limit as b approaches infinity. And we have also have this 1 too, was our boundary. So we have this b minus a 1 substituted in our lower term. So we have this difference. And now we look and see what happens as b becomes large, depending on what p is equal to. When p is greater than 1, this exponent, when p is really close to 1, this exponent is going to be very close to 0. But then greater than 1, it's going to be a negative number. And when p is positive, this b goes into the denominator, and it causes this left-hand side to start becoming very, very small as b approaches infinity. Now, if p is less than 1, like p is a negative number, you end up with a positive exponent, which means b stays in the numerator, and as b approaches infinity, the numerator becomes very, very large and approaches infinity. And so what it means is that in a case when p is less than 1, the limit becomes infinity. The integral is infinite. There is no answer for it. It's insoluble with those boundaries. The integral would have a value. The result would be infinity, not a constant number. But for the case where p is a number greater than 1, the limit becomes the 0, and we end up remaining with 1 over p minus 1. So that's a rule that you can follow to find what this whole family of integrals would equal to. So integrands with vertical asymptotes. This is the case of the type 2 improper integrals, the other half of the family of improper integrals. And that's where we have asymptotes within our limits of integration or at the boundary of our limits of integration. An asymptote would look something like this as we draw our graph. Let's say this is our x-axis and that's our y-axis. So we have this asymptote here where the function is undefined, usually division by 0, in this region. And let's say your boundaries are right here and right here. Well, basically what you have to do is you just take this value and you just solve one integral from here to here. You take another integral and you solve it from here to here as two different indefinite integrals. Basically the process. Same is true if the boundary happens to equal the asymptote. Then you would also need to, then your indefinite integral, your improper integral would be the same as we had done already. And so we have this integral from 0 to 4 of dx over square root of 4 minus x. One of these values substituted in for our integrand, value x, will cause a division by 0, and that's 4. You substitute 4 in for x, you get a division by 0. And so you have to avoid 4. You have to avoid, you also have to avoid certain numbers too, because you don't want to get a negative number under the square root. Real numbers make real answers. And if we get a complex number, not very helpful to us. So we want to approach 4 from the low side. We want to go up to approaching 4, not down from high numbers to going lower. So this is a left-hand limit starting below 4 as we go from 0 to b of this integral. And we solve that. This is an integration by substitution. So let's solve that integration by substitution. It's sort of a fast and easy one. You can do the whole integration on one slide. U equals 4 minus x, du equals negative dx. We have the integral of u to negative 1/2 equals the negative 2 times u to the 1/2. And so that's our integral. I'm not certain about something here. I think that's supposed to be a positive here. Oh, no, that is supposed to be negative. Because of our dx is a negative dx from our substitution. So yes, that negative is correct. And then we substitute u in to bring this back to a function of x again. And you basically get negative 2 times the square root of 4 minus x. That's what 1/2 power does. And now we take this to a limit. So here, what we have on top here is the limit of this interval. I'm going to draw parentheses around here just to make it a little bit clear that we're looking at this whole thing. And so we evaluate this negative 2 times square root of 4 minus x from 0 to b. And what you end up with is that this is equal to 4. And so and below here I have the graph of y equals this 1 over 4 minus x quantity square root with the integral shaded. The summative area of this is 4 because as we get closer and closer to 4, the area added within this region under the curve becomes very, very, very small and insignificant compared to the area we've already got. This becomes very close to the line of x equals 4. And so there's the area underneath this curve that's added in is very small, and it converges an exact number of 4. So we have here integrands with vertical asymptotes. If f of x is continuous from a to b, then but it's discontinuous at the border, at where it starts, they just substitute in a variable c as c approaches a from the positive side. So you're not actually going to a, you're getting close to a, you're approaching a, and that variable that approaches a is c. Same is true for the high side. You approach the high side from the lower side, so you do a left-handed limit as you approach upwards towards that b value. If the discontinuity is somewhere in between the a and the b, you need to break this up into two integrals with this asymptote point c, where the discontinuity is as your boundary between these two integrals. At c is where this discontinuity is, and this is how you dance around that. And you deal with these just as you would with these guys, like that. And if you have more than one discontinuity, you would need to break it up into further pieces, like A to C for one discontinuity, then from C to D for another one, and then later on to D to your upper limit b. And each of these would represent a discontinuity in your graph that you'd be needing to avoid. I try to draw like an asymptote here that you would have to avoid at the asymptotes at C and D. And so if the limit is finite, it converges. If the limit does not exist, the integral diverges and does not approach any given value. So here's an example. We have this function. We're integrating it from from negative 8 up to positive 1. But at 0, it's undefined because that's a division by 0. We will have a 0 in the denominator. So this curve exists in two separate pieces. Because a curve is in two pieces, separated by this asymptote, we have to have two integrals. And integrals are broken up at that point of 0. Negative 8 to 0, and then 0 to positive 1. And then each of these integrals, we do just the way we've done before. This integral, it's undefined at 0, so we're going to have to approach this 0 from the negative side. So it's going to be a limit as b approaches 0 from the low side. And this one is going to be as b approaches 0 from the high side, the right-hand limit. So we can formulate this into a limit where we have this b as our limit variable. We have these two different math problems we do. They're two very similar math problems. You solve this indefinite integral and you substitute it into both, and you take out 2 at the same time. And so what is the integral of dx over x to 1/3? Well, it looks like your standard power rule integral, one of our favorite ones we do. You raise that, so that's basically x to negative 1/3. You raise negative 1/3 by 1, adding one dimension through integration. You add one dimension to it, you get x to the 2/3. And you divide by 2/3, which involves a division of a fraction by a fraction involves multiplying by the reciprocal, 3 over 2. And so that's your integral. Now you evaluate this integral for the two boundaries we have here, negative 8 to b and b to positive 1. And so we're going to end up with 4 terms here. The left-hand limit substituted for b minus substituted in for negative 8, and then the same for the right-hand side. I color-coded these to try to clean this up a bit. What we end up with here is a cubed root of 64, because x to 2/3 is basically x squared taken to the 3rd power, 1/3 power. And so it's going to be negative 8 times negative 8 is 64, and then 64 to the 1/3. And what we have is our negative 3/2 due to this, because the 8 was negative. And so, because you could likewise also visualize this, it's actually also correct to say the cubed root of 8 squared, you have a negative. And then minus this, so, oh wait, no, I got that backwards. I didn't think that was right. Yeah, that negative is because it's subtracted. And our b is our higher one. So this is positive limit of 3 times b to 2/3. Now when b approaches 0, this is also going to approach 0. And so would this. This would approach 0. And so you have negative 3/2, and you have a positive 3/2 here. I just went on and factored by 3/2, this is actually equal to 4, and this one is the 1. 4 minus, 1 minus 4 is going to be negative 3. So these are equal to a 0. This one's 0. And this is negative 9 over 2. That's the value of your integral. That is absolutely correct. And so we're almost done here. Just one last thing. We've got a couple tests we can do. This is something that they're just throwing in while we're on the topic. If you have an improper integral of type 1, and let's say you have two functions, the f of x and g of x, and f of x is always less than, but possibly equal to, g of x. Well, what it says is that if g of x, the larger function, converges, it forces f of x to also converge. So it makes sense. And if you have this lesser function, the function that's always less than, which is f of x, and if it diverges, the larger function must also diverge. And so that's really what this is stating. It's sort of makes sense when you think of it like that. And they talk about a test, and that is if you'd have two functions, f and g, and they're both continuous across an improper region, like a to infinity, if the ratio of these two is a constant number as x approaches very, very large, then both of these improper integrals would either both converge or they would both diverge. So if you happen to know that f will diverge or converge by a test you've done, you can do this to test to see if g of x will converge or diverge. So you'll know if it actually will approach a value or not. Now, if you have f of x and g of x and you don't know if either one of them converge or diverge, then this limit comparison test won't do you a bit of good, because it's only useful if you happen to know if one converges or if one diverges for certain. Then you can use it to test for another one too. And so that's a test you can do. You'll see more of these last two theorems in chapter 10 when we start dealing with sequences and series. There's actually tests for sequences that are very, very similar to these, the limit comparison test and the direct comparison test, which in chapter 10 they talk about a test, a theorem called the sandwich theorem, where if you have a function that converges upward to a value, you have a function that converges downwards to a value, and if you have a function that's always the less than the upper one, and it's always greater than the lower one, that this function must always converge to the same as the lower one or the upper one. Sandwich theorem, very closely related to the direct comparison test. You'll see that coming up, so you won't be completely strange to it. This is more akin to a test we'll call the ratio test. That comes up later too. And so this stuff won't be entirely foreign to you. Coming up, you'll see things that will resemble this. So have fun with this. We'll talk about this more tomorrow.